Yeah, so today's presentation, as Giuseppe mentioned, is about really the problem that many people struggle with understanding machine learning models. And that's probably not coming as a surprise because some of them are really complex. We hardly understand how they've been created, and then we get like a bunch of formulas or things out there which all depend on each other, and that makes it hard. But this lack of transparency actually leads to a huge problem. We'll discuss this and also discuss a couple of techniques to overcome this. But there's one even bigger problem when it comes to the interpretation of machine learning models, and that's what we call the hidden black box. And I will discuss this problem. Luckily, the solution is kind of simple to overcome that problem as well. So I hope there's a couple of practical takeaways out of this here as well. Good, so let's get started with the one thing which makes me kind of angry, really, that I spend a lot of time building machine learning models myself, and a lot of my colleagues did, and then many of those models, they never end up in production. So this is a quote I got from Gartner, some Gartner research a couple of months ago. Gartner said that, well, they did some surveys that 60% of all the models which have been intended to be put into production actually never see the light of the day. And that's pretty horrible. I mean, there's gazillions of models where we just play around, we want to generate some insights, and that's okay. We accept that they probably are not going to be used in a repeated fashion. But 60% of the models which should go into production, they still don't go there. What is the reason for that? So again, if we look a little bit deeper, Gartner claims like, hey, look, it could be that there's a lack of tools. Maybe it's not that easy to take a model generated and put into production. And yeah, I agree to some degree at least, especially if you're coming from a more, let's say, coding-centric approach to data science. But at the same time, I would argue, if you're smart enough and your team is smart enough to use coding to generate machine learning models, I would bet that the same people are also smart enough to actually use coding for putting the same model into production. So I have a hard time to really believe that. Plus, there's a lot of solutions actually out there. So I don't think the lack of tools is the only thing. And Gartner themselves, they actually went on and said, like, well, maybe there's a bit of work in silos here, and the people who actually need to sign off that a machine learning model is actually disrupting the business processes, maybe they're not involved enough. And I would agree. I've seen that a lot, in fact. But there's another problem if they're not involved. They don't really understand what is going on. And that, if you don't understand what is going on, and then you need to decide, let's use this model and disrupt our business here, that typically leads to a lack of trust. And if you don't trust something, you're not going to use it. And that is something which is really very, very, well, human to say. So that is where we start. So let's actually analyze some data together here. And I'm picking a use case or a data set here which is very close to our heart, literally here. This is about predicting heart diseases. Why is this important? Well, if I have some sensor data or let's say some blood samples, and I could predict that somebody is more likely to suffer from a heart disease, maybe there's still enough time for this person to change their lifestyle. Did somebody just say bad blood? Yeah, maybe not. But that is the basic idea. So that would be fantastic, right? Let's have a look at the data, then we analyze it, and then we use this for the rest of the presentation as an example here. So here's the data set. For those few of you who've never seen machine learning before, here's the Machine Learning 101 for at least one important part of ML. On the left side, those blue-white columns, those are features or attributes describing our patient. So each patient is a row in this data set, and then we have information like age or gender or if there's a certain type of a chest pain. And this is all encoded in this data. So we know something about our patients on the left, and then there's one specific column on the right, the orange one. That's what we call the target or the label column. That's the one we want to predict. And the goal for machine learning, or not for all machine learning, but for a big class of machine learning methods, is to take the information in those blue-white columns and create some model, a formula, a collection of formulas, to actually calculate the outcome in this target column. So is it yes, is it no, what is the likelihood? And that is what we try to do. So let's now do that together. So we will build some models, and I'm going to use RapidMinus order model for that for two reasons. I could show you a bunch of R code lines, but then we run into a bit of trouble potentially anyway, because then we don't even understand how the model is generated. So it's a little bit more visual, that's good, and also I might be a little bit biased, but I just love this thing. So let's look at this data here. It's the same data set as before. Only difference is the target columns on the left. So we could cluster the data now or do other stuff, but in fact, we want to predict this column, so all is good. Let's step over this view. This next step is actually kind of interesting because it tells us right away there's a couple of data quality problems. So you see this traffic light here. So there's a couple of columns like the ID column, for example. They're not going to be helpful for building a model, so RapidMiner suggests to take it out. So good, let's do that. But then there's this one yellow column, and this is a little bit more interesting because RapidMiner actually says, I don't know about this one looks suspicious. And what makes this column so suspicious is it's almost too helpful to actually build any models predicting heart disease. And what is the name of this column? It's previously diagnosed. Yeah, duh. If you had a heart disease before, you're just more likely to get another one just because your lifestyle is already what it is. So yeah, we could keep it in, but then all the models would probably say like, hey, if you're already suffering from heart disease, you're going to have another one, and that's not very helpful if you want to predict the first one in time. So I agree, this is suspicious, let's take it out, let's move on. So now RapidMiner suggests a couple of models here in this middle column. Let's keep the selection as it is. I could turn on automatic feature engineering, feature selection, and feature generation. The thing though is, if I do that, then we would probably generate between 150,000, 200,000 models for this data set. That takes roughly an hour. I don't think we want to wait that long. So let's keep it off for now, but we will come back to this later. All right, let's keep the settings as they are. So we now start running the models. First results are coming in. First model here is naive Bayes, 86% accuracy. You can have a look into different quality measurements here, whatever accuracy, error, AOC, you pick it. Let's just stay with accuracy for the sake of simplicity here. So we get a lot of models built here in the background. So 45 have been tried, 82 in the background right now. As I said, with the settings I've been choosing, it should be relatively fast. And we can see a couple of things. First of all, naive Bayes doing a good job. The general linear model, actually with 88%, pretty much the best so far. Let's see, gradient boosted tree is coming in right now, 87, not as good. But look at that, decision tree, 62%. That doesn't look good, and that's a shame. Why? Because decision trees in general are considered to be very understandable. So let's have a look into this model here. Yeah, it is a simple model, it's easy to understand. It only depends on two columns, ST depression, whatever that means, I'm not a doctor, and maximum heart rate. It's not doing a good job. I mean, to be honest, even if I know those two things, it still ends up in a situation where it's pretty much a coin flip. So I hope doctors are doing smarter things than that. But I definitely am not ready to trust my life to this model. And this is a bit of a problem. So other models, for example, the GLM was much better. And this is a little bit interesting. This is a linear model. And yes, I can look into this model. I can see, for example, what are the more important factors by sorting the coefficients here. But let's be honest, in this group here, who of you know the exact formula how the linear regression model here is taking those coefficients and turn them into a classification prediction? Well, show your hands. Not too many people at the same time. 1, 2. Okay. It's considered to be a simple model, a linear model. Excel can do this. And still, we don't really fully understand how they work. And that's the core of the issue here. Typically, in machine learning, the better models are more complex. So if the model has better accuracy, prediction power, then it also gets bigger, more complex, uses more elements, and it makes it harder and harder to understand. And we apparently already struggle a bit with decision trees, linear models, and other supposedly simple models. What that turns this whole thing into is like, all I see is, I have this black box in the center here, I throw some inputs in on the left, and I get some outputs on the right, and then I hope for the best. Brilliant. This is a problem though. I mean, sometimes human life depends on that, sometimes just millions of dollars. And I'm not sure, most people then, if they see this model, so a couple of data scientists go into the basement, hack something, 6 months later they come out, and here's the model. Trust it, change your business. Let's automate our decision making from now on. Many people struggle with that. And that is exactly the trust issue, and that is what I believe is one of the core reasons why models are not put into production in the first place. So what can we do? Here's three pieces of advice, and I'll go into the details in a minute. So first of all, I think we really have to start to focus much less on prediction errors alone. I know there's Kaggle out there, and that's how we train data scientists in colleges right now. Hey, let's press out another 0.1% accuracy, but it is the wrong approach. You will see in a second that there are alternatives, and they're actually better. Another idea we can use is we often know something about our business. We know something about the use case we're working on. And this prior knowledge, that is something we can test the model with. So we can feed things into the model like in a simulation process and see how the model behaves and if that confirms what we believe to know. And that again, if I do this a couple of times, can help building some trust. And then last but not least, if you do the simulation at scale, then you can see that this actually naturally leads to an algorithm which is widely used today for explaining models, even complex model, which is called local explanations. And we will see this later. So let's start with the first one, focus less on prediction errors. And yes, that is something many data scientists hate when I say it, and I still believe it is the right approach. So we're coming back to the heart disease data a little bit later, but for now, I will introduce a couple of other data sets as well. Just they're a little bit simpler. It helps me to bring the point across. So here's another data set. It's not a classification problem like before, but we only have one dimension, x, shown here on the x-axis. And we know values for this dimension, and we would like to predict the numerical outcome shown on the y-axis here. So goal is, for our machine learning models this time, is to find a function so we can actually, given any value of x, predict the outcome of y. So quick example here, if the value for x is 5, Giuseppe, what should be the prediction of the model? 10,000. Thanks for playing. Thing is, yeah, so you get the idea. Okay, so this is what we try to achieve. Let's start with a linear model. And I'm not expecting a lot because this is clearly not linear data here. It's not a linear relationship. So there's those curves here. There's this strange peak. There's also some level of noise. It doesn't look too easy. But if I actually train a linear model on this one, well, it's doing it the best it can. It just puts the linear line across this data set. And yes, there's 3 areas where the model is actually pretty good. But all the rest, the model is not obviously not perfect. Well, I said let's not focus too much on error rates, but at least let's measure them. Here I calculated the relative error, and this one is 39%, so not very good. But we have a baseline. So if linear models are not good, let's try a nonlinear one, for example, a decision tree. And the decision tree here is actually making a pretty good job. It shows some level of noise. You can see those red points, they move around there a little bit. But it really didn't get the concept of the peak, so there's those plateaus at the center and this random blob up there. It didn't really get it. So, but the error rate is much lower, 6%. So that looks better, right? And if one tree is doing a good job, well then let's build dozens or hundreds of them. There's a technique called gradient boosting trees. Here, the idea is I start with one tree, and then I build additional trees on top of the first ones, and each additional tree tries to focus on the areas where the previous trees made most mistakes. And if I do that, it's less noisy, it gets the peak, it gets the oval shape, and the error rate is probably as good as it can get with 4%. So that looks pretty good. Well, obvious then, right? We have gradient boosted trees with 4% error rate, decision tree with 6%, and the gradient boosted trees are better than the decision trees, and the decision trees are much, much better than the linear model with 39. Clear case, gradient boosted trees it is. Let's put it into production. I see the first person already like shaking their head, and it is right. I would never just do that. Why? If I look at the models themselves, it becomes pretty clear. Let's start with the linear model first. This is the model. Yes, it's not really doing a fantastic job, but that is the whole model. The prediction of y is calculated with 817 times x plus 17,347. Yes, it's not perfect, but at least I can learn something from that. So for example, I can look at this formula and say, if I double the value for x, the value of y increases by roughly 1,600. And that's something I just learned. And that might be of value. And I can understand this, and I can check if that makes sense to me. So yeah, not a great model, but at least I can learn something. But decision trees are supposed to be simple as well. And we saw an example earlier. So let's have a look at this model then. And that's not a graphical arrow, that is also the complete model. And it has hundreds of different leaves, and it's so small here you can't hardly see it. So let's zoom in just on the area on the right here. Yeah, that whole tree looks like that. If x is bigger than whatever, 16, but it's smaller than 16.5, but bigger again than 16.2, and then smaller than 16.4, then it's 280. I don't know, I can't learn anything from that. I actually have a hard time to understand that thing and grasp the whole tree. And that's just one tree. With gradient boosted trees, things are even worse because that model with 4% error rate has 500 of those trees and they all depend on each other. And I'm doing data science for 20 years now, and I tell you, there is absolutely no chance that I can understand anything from that model. Okay, so the clear case is actually no longer that clear. So let's say I put this thing into production and I need to trust it's going to work like that forever. I might struggle with making that call, really. And that's the trust issue. So what else can we do? Well, good news. I have an alternative here. I have a fourth model for you. And look at this model. It's a beauty. It gets the shape, hardly any noise. It got the peak. I mean, it looks fantastic. What did I do? Did I use even more trees? Or deep learning? Or just magic? Nope. I just used another linear model. But this time, I also did some automated feature engineering. Remember what I didn't activate earlier in RapidMiner Auto Model? So if you do activate this, we actually can generate additional columns in a nonlinear way based on the original column X. And then the linear model can actually be trained in this new space. And as you can see, this model looks pretty good. And it's supposed to be simple because it's linear, and the error rate is only 5%. And I would claim, I didn't do the test, but it's probably the same error rate. It's probably not statistically significant, the difference between those two, GBT and this one here. So that looks pretty good, but just look at the model. I mean, I can look at this thing, I can understand that. I mean, it's 10,000 times absolute value of x, and then 7,500 times x, and then absolute value squared, and then 705 divided by absolute value of x. This, by the way, explains the peak at the center. And I mean, again, this is random data, I artificially generated it, but it could come from some, let's say, some production process, and I could be an engineer looking at this and say, ooh, it's absolute value squared. That makes sense. And that little sentence changes everything. So they probably wouldn't know that it's exactly 7,565, but there's a good likelihood that they had a bit of an idea that there's a quadratic relationship maybe, and that helps building trust. And this is a fantastic model. And by the way, it's also faster to calculate the simple formula for scoring compared to calculate the outcome of 500 trees all the time. So there's a lot of things to consider next to just error rates. I always recommend to balance error rates with understandability from the beginning. And if you do this and you're a bit creative, you can actually generate fantastic models using good old 200-year-old linear regression in many, many cases. And I rather would go with that one than the most fancy latest stuff, which has really zero chance to be understood by anyone. That's not to say that there's not a place for those other models as well. There are use cases where understandability is less important, and then the 0.1% accuracy is important, and if that is the case for you, and you can accept the fact that you can't understand anything, go for it. But in my experience, in reality, in many cases, think about regulated governed businesses, you probably want something like this. Anyway, so that was the first one, the biggest one. Let's move on. Using simulation to confirm prior knowledge. I love this. I always did, and it's one of my favorite little tools here. So what do I mean here? So even if my machine learning models behave like a black box, get some input, I get some output, there's one thing I can do. So I'm not a doctor, but I have a friend who is. So I could go to her and ask her, look, I have a patient, let's say 54-year-old woman. She unfortunately suffers from asymptomatic chest pain type, has a colored vessel level of 0.695, whatever that means, and a maximum heart rate of 143 and so on. And I could now ask, before I even used the model, the doctor, what is your expectation? And she might say like, ooh, bad news, that doesn't look good. I think high likelihood to suffer from a heart disease soon, let's say roughly 80%. And that is her expectation. And then I feed this data into the model and I see if the model behaves like she expects. And if I do this 20 times with her, and in 19 out of 20 times the model is behaving like her, she thinks like, yeah, that's like another doctor. This model behaves like a doctor. That's fantastic. So this really basic idea, since we're not doctors, we can still try ourselves. So I think there's one thing we believe to know about heart diseases, that high levels of cholesterol are not a healthy thing and lead to a higher likelihood of cardiovascular diseases. So let's actually try this in our model we've created before. So we still have the heart disease data here. Let's just go whatever with the first model. It's a knife-based model, not super hard to understand, but still most people wouldn't. And then there's this little simulator here. So the idea here is that on the left side, it's probably hard to read from the back, but I will explain it. On the left side, we have all the inputs for our patients. Basically, all the columns in our data set are here, and it's pre-initialized with the average patient data. And on the right side, let's focus on the top half first, the blue and orange bars. We see what the model behaves as the output for this patient. So good news, right now we believe that the likelihood for heart disease is 14% only. So the really good news is your average patient has a higher likelihood for survival. I think that's good for all of us as humanity in general. But let's now play around with the cholesterol level, which is down here. And while I'm doing this, pay some attention to the blue bar on the right. So let's bring it down first. So I see how the current level behaves compared to all the data we know about. Let's bring it down. It's probably hard to see, but you can see it's going down a little bit. So let's go the opposite direction. Let's bring it up. Ooh, look at that. The further I bring it up, the higher is the likelihood for getting heart disease. Let's crank it up all to the right. Now I have a dead patient. 53% of non-survival. Well, that's also a cholesterol level of 470 now, which I guess is not very healthy. But the thing is, the model behaves like we expect it to behave. And although I'm not a doctor or an expert for this, at least there's one thing I believe to know, I can check and yeah, that makes sense, and that's good news. So this technique really can help me to build some trust. But I did this now for 5 or 10 data points. Can we use this technique of simulation also, let's say in a more algorithmic way, and use this idea to explain pretty much why a model is behaving like it does? And that's what I'm going to explain next. And another data set now, this time again a classification problem, 2 classes, green and blue. And we have 2 input dimensions, x and y, on the corresponding axis. And that looks like a simple problem, right? I mean, for us human beings, we look at this and think like, yeah, that's like a checkerboard pattern here, and I don't know, that shouldn't be too complex. And you're right, it shouldn't be. But there's obviously no linear model you can't put a linear line in there to separate the 2 classes anywhere, so that's not good enough. So let's try something non-linear. For example, again, our good old friend, the decision tree. And if I look at this tree now, it looks relatively complex given that the data set is so simple. So why is that? Well, the main reason is that when we look at this data, we always focus on one little area, let's say the area in the bottom right, and say like, well, when the values for x are high and for y are low, then it's green. Yeah, but now we only explained this little part of the data set, but the model needs always to explain everything, and that's where a lot of the complexity is coming from. So, but what is the model doing if I only look at a single data point? So let's say this one here. I hope we can agree that this is clearly a green data point. So now it's your turn. Out of the 2 dimensions, x and y, which one do you think is more important to determine that this is a green point, x or y? Even if you don't know, you have an only 50% chance. That's better than in most casinos. So feel free. Y. You say y. And why are you saying y? It's next to the boundary, meaning if I change y just a little bit, then it flips the class. But if I move x around a little bit, it wouldn't impact the class at all. So for this point, y is in fact more important. While for the other point here, on the left now, x would be more important because if I change x a little bit, the class flips, while if I change y a little bit, it doesn't really matter. So it's not very important, the specific value for y. And this basic idea is something we can now combine with the simulation idea we had before. Let's go back to the first point here. Let's just generate artificial data points around this one we want to explain and ask the model what are the predictions for all those data points. And after we get all those predictions, we can actually check, well, which of the 2 dimensions had more influence, x and y, as we just did as human beings. And this super simple idea, you probably would assume, since machine learning is around for 50, 60 years now, that this is a very old and very well-known technique, and in fact, it's not. The research paper describing this technique has only been published in 2016, which is still blowing my mind, because I kind of believe, since I was doing simulation a lot around machine learning models, that everybody would kind of think about this. But nobody actually did. So LIME is the name of the algorithm. There's a couple of different variants and algorithms out there. LIME is the one which was published in 2016. And it's basically doing this simulation at scale idea, generating those artificial points, taking the predictions and measuring the impact of the different values. In RapidMiner, by the way, we generated a new version, a different flavor of LIME, because the original one can only work on numerical data and for binary classification problems. And we kind of extended the whole algorithm so we can work with all kinds of data, also for multi-class classification problems and also for regression. And most importantly, it works in real time. And that's, by the way, the reason why, if I play around with the cholesterol level, so right now you see the cholesterol has some influence. Green means supporting the prediction yes. If I bring it down now in real time, you see how this flips over because the prediction just flipped. So now it's contradicting the prediction of no. And if I bring it further down, it actually drops out completely out of the important factors, because all of a sudden, at a certain range, the cholesterol is no longer that important for this particular prediction. So we can also show this pretty much for all the rows at the same time. So dark green means it's strongly supporting, dark red means it's strongly contradicting. So at least, even if you don't know how the model exactly works, for every prediction at least you can get the explanation, why is the prediction made. So there you have it, right? That's a good set of techniques. We should be fine, focus less on prediction errors, use simulation, use local explanations, all good. But there's one more thing. And that is what we call the hidden black box. And this is, in fact, in my opinion, the biggest issue I've seen over and over and over again. What is this? For all you know, the models I created and showed you so far, let's say on the heart disease, could be the outcome of some random process, or even worse, out of a faulty one. You wouldn't know. All you saw me doing was loading in the data and clicking 5 buttons. You don't know what I did to the data, how did I transform it, how did I generate the model, did I do some feature engineering, did I actually correctly validate the model? Most importantly, did I correctly validate the impact of the data transformation, something pretty much all the automated machine learning products are doing wrong right now? You have no idea. I mean, am I that trustworthy? Are you taking my model now and like, oh great, thanks for the simulation, now let's go into production? No, I'm not. I kind of am, but not really. So let's actually have a quick look at a different model. I go into a different part of the RapidMiner platform, which is kind of a process designer here for visual workflows. And I created a workflow here, and I'm now doing the auto modeling for you. I load the data, I tell RapidMiner which is the target column, and then all the magic happens inside here, but I'm not showing you the details yet. Here's the data. Now I built a model, and since I don't have enough time, all I'm going to tell you right now is this model has an accuracy of 94% almost. Okay, it's up here, very small, but trust me on that. And it's a linear model, so it's easy to understand. So look at that. We have an even better model. Just for comparison, the models we have seen so far had 83 to 88%. Doctors, by the way, are roughly at 82 on that data, so it's actually already good. But this is 94%, and it's a linear model, easy to understand. Fantastic! Let's put it into production. I become a doctor using this model. I will heal 1,000 patients. I used this on 1,000 patients, and 3 years later I realized I accidentally killed 100 of them. Oops. Why is that? Because I made a couple of mistakes. I didn't show them to you. I was hiding them, in fact, from you. And I'm not going into the details in the interest of time, but I normalized the data and didn't validate correctly the impact of the normalization. I did feature engineering and optimized for accuracy, but introduced some information leakage as part of that accidentally. Didn't want to do it, but it happened. Made another small error for the validation. If I correct all those things, so this is here the same process, just I'm doing it right. I'm not doing this mistake. So it's pretty much the same thing, and I run this again. What we will see now is that the outcome of this model, it's still a linear model, but actually the accuracy drops down to 83%. It never was higher. It only looked better, and this is the thing. You can do many, many mistakes, and if your folks are trained to actually improve and focus on error rates, they will do whatever they can to make their models look better. I have 95%, I have 96%. But then you put the model into production, only then you will realize that the model never was that good, it just looked that good, and the accuracy drops down, something which you could have been seeing if you did it right, to whatever it was all the time. And I said, I applied this model on 1,000 patients, the accuracy dropped by 10%, that's the 100 probably patients I accidentally didn't treat or treated and shouldn't have been treating. Not a good idea. So, this is the hidden black box. It is the model creation process. Don't get me wrong. I love automated machine learning. It's a great productivity tool. It's a fantastic tool to empower more people, citizen data scientists, everybody to create machine learning models and use them. I love it. We at RapidMiner put a lot of efforts into this. But you can't allow the introduction of this hidden black box. Because if you don't really know all the details of the data transformation, feature engineering, validation, the details, not some stupid Word document describing on a high level what happens in the background, the details, the exact details. If you can't get that, how could you ever put this model into production? How can you talk about governance? You're in a nightmare then. By the way, the solution is pretty simple. And then, yeah, you will see. If I like this model, this Bayes model here, well, just click on open process. Well, here you have it. All the data preparation, all these things. Maybe you can't understand that, and that's fine. But somebody in the organization will be able to do that and is able to do the quality assurance. All right, let's wrap it. 3 key takeaways, really. First one, you should reduce the focus on errors alone, at least. I mean, of course, you want to try your best to build a good model. But balance it with understandability, robustness, runtimes. There's a lot of things to be taken into account. Also be a bit creative, and you will be able to see that you can actually build fantastic models which are almost as accurate, sometimes equally accurate, but more understandable. You need to spend at least as much time on explaining models than on creating them. The second I see people not doing this, I know already that they focus way too much on error rates. It's a clear signal to me, like whenever I see that. You need to bring the stakeholders in, keep them on board all the time. Even if your model is 0.1% more accurate, oh, that's so much more value. If it's not in production, the value is 0. So what's the point? So, explain your models, and last but not least, at all costs, there is never an excuse. You have to avoid the introduction of this hidden black box. If you don't do that, I mean, you can just go to a casino, you can roll dice, it's the same thing, really. I think it's totally not acceptable. And it's actually also not acceptable from a governance perspective, so why would you ever accept that? I don't. All right, we put a lot of efforts doing this right. I think I need to come to an end here. We're pretty awesome. Yeah, whatever. I don't have more time to say that, but I started with the Gartner quote. Here's another Gartner quote. 6 years in a row, we have been recognized as a leader in Gartner's Magic Quadrant. Really proud of that. That's thanks to our 500,000 users. Some of them might be in this room here. Thanks to you. And if there's any questions, please let me know. Thank you.
Great presentation. I just had a question. When optimizing accuracy and interpretability, how are you accounting for recall and precision? Because your false positive, false negatives are oftentimes more important than accuracy. And so how does that affect the interpretability of your model?
Well, typically not that much, because it's just like a different criterion you're going for. So let's say you know already, for example, the cost of certain error types or whatever, then you can turn, instead of optimizing for accuracy and balance the accuracy with understandability, you would in that case just say hey, look, I need to go for precision for this class, or I need to go for recall of that class, or I can even, since I know the costs, I can actually turn the whole the confusion matrix plus all the cost rates, I can actually turn this into a number I can optimize for. But at the same time, while you're doing that, you still have the other objective of actually optimizing for understandability. I don't have it readily available, I guess, but especially if you do the feature engineering in RapidMiner, for example, we even show you this whole trade-off on one curve. So you can, for example, say, here's my costs, here's all your error rates, and then you have basically the different feature sets, and you see this Pareto front of the different trade-offs between understandability and optimal, in this case then, error rates or whatever it is, precision recall. You can pick it, whatever should be optimized. So it doesn't change it that much, to be honest, what you're going for.
I do have one question, because this to me is extremely relevant to the kind of maturity of the field, because it's going from mostly people in the lab you know what I mean, to going into the real world. And so, you know, it needs to be put into question the legitimacy of that. And in fact, you know, I would advocate for like getting more of the domain expert, domain knowledge. In feature engineering, for sure, you know, you have to be more, do the hard work of interacting. And in fact, AI is interdisciplinary, not just because it borrows from many disciplines, but also because it connects with all the other disciplines. And that's, and you know, and to some extent, as a community, I think we should also consider, and I wonder what you think about that, almost the creation of a standard, like a trust scorecard or something like that, that we can all agree upon in order to really accelerate the adoption of these techniques that you're discussing. So.
No, I couldn't agree more. And actually, I think this is a perfect event for actually starting this movement here, the Open Data Science Conference, because this kind of standard can only be introduced with a certain level of openness. There's no chance whatsoever if this is too proprietary, if it's too hidden. And this is, by the way, coming from the founder as a software vendor, okay? So we try to sell our IP and not make everything open, surely, because we want to make some money. When it comes to algorithms, processes, everything for us, for example, is open as well. Why? Because we otherwise could never get to this level of standardization I'm hoping we can get to. But that's technology. I think the other aspect, and that's probably what you meant by maturity, is us, is the people. That we need a bit of a culture of change, really, and a bit of standardization there, and processes, frankly. And I think there's still some way to go, to be honest. But yeah, we get there.
So when we're trying to gain trust, we usually are dealing with people that are not very tech savvy. So they need to make a decision upon using a model or not, but they don't really understand all the options. So what is the difference between machine learning, deep learning, etc. And maybe in some cases it would be better to use a logistic regression, some linear model, or maybe a decision tree, a simple one, whatever. It could be better than a deep learning, neural network, etc. And the executive just reads an article that says that deep learning is the new hot thing, it's the best model in town. And he just asks us, so are we using this, new techniques, deep learning, etc.?
Yeah.
How do you address this when people that are not very tech savvy, they're looking for the new hot things, they want to make sure they're using the best possible solution, but in some cases, the best one is not really the most hot topic on the moment.
In many cases, actually, yeah.
How do you address this?
So first of all, we never know before we try, because in some cases it's not the best, in other cases it is actually, and I always like to present all the options. So especially, I mean, I was working as a consultant for many, many years, and as a consultant, the first thing you learn, if the client asks you to do X, even if you know better, you just do X and you do what you think is better, and then you provide both options. Like, look, I did what you did. I also just yesterday came up with this idea. It only cost me an hour, even if that's a lie. It only cost an hour to try this other thing, and look at your idea was actually the reason bringing up this other idea I had, which turned out to be even a little bit better. Do it if you're asked to do it, and show the options, but explain all the pros and cons. Explain that the deep learning model, even if it is actually better in accuracy, but look, do you understand what's going on? Are you good with not understanding? Because I have this alternative here as well. So there's always multiple dimensions. It's not as simple as Kaggle contests make us believe the world is. Nothing against Kaggle, by the way. But it's just like, no, it's not just like the best model is the most accurate one. There's so many dimensions. You can almost make like a scorecard, like, hey, in terms of accuracy or whatever the performance criteria is, we have here a ranking here. In terms of, let's say, understandability, this is what we believe is most understandable. In terms of like how fast is it for scoring, that can be important. One of our largest clients, they need to generate 10 billion predictions within 1 hour every night. Well, yeah, maybe deep learning or gradient boosted trees are a little bit more accurate. It doesn't matter because the infrastructure they would need to actually calculate them all is too big. So all of a sudden, there's other factors, I guess is my point. So do them. There's always the case in data science. You need to try out anyway, otherwise you wouldn't know what is the best. Include what you're asked to include, but then show the options and explain clearly why you think one is better and what is your recommendation to go with something. And I have made perfect experience with that when I was working as a consultant, which I no longer do that often, but yeah, I think that's one way to address this. Last one? Absolutely.
Thank you for a wonderful talk.
Oh, thank you.
May I ask, in the example you showed with the heart, how many features you engineered, and did you use any feature selection method to kind of narrow them down through the process?
In the one I actually showed here in the auto model live today, I didn't do any, neither feature selection nor feature generation. If you want to, when we wrap up here, I can restart this whole thing and start this. Typically, for a data set of that size, I would estimate, you can tell how much time you want to give. Within 10 minutes, for every 10 minutes you give, you would typically evaluate roughly 4,000, 5,000 different feature sets, subsets. So the original size was like 20. So you take pretty much combinations out of the 20 original ones. You go every 10 minutes, like let's say a couple of thousand. If you also activate feature generation, the way how we're doing this is a pretty smart one. We do this with a multi-objective optimization approach. And the point is that we don't just randomly generate stuff and then throw it away again, or even worse, keep them in. Because that leads to something we call feature bloat, which basically makes the feature space bigger, 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 and then it gets easier for any machine learning model to learn whatever they want to learn. So you move the problem of overfitting from machine learning into feature engineering by doing that. That's a pretty bad idea. That's actually was the topic of my PhD, how to do it in a better way. And we obviously then put it into the product. Happy, that's a presentation on its own though. Happy to actually discuss this at more detail. Typically for that data set, I would say we generate 150, 200 features, but we probably end up with only a handful, if at all, in the ultimate final set. So I'm happy to show them.
Which feature selection method do you use to end up with this handful?
If
you can do it, provide a very quick answer.
Evolutionary.
Continue.
Yeah, it's a mixture of genetic algorithms for the selection part and genetic programming for the feature generation.
Thank you, Ingo. Thank you very much.